In this video, we're continuing with Chapter 7 of the chemistry textbook. In the previous video, we went over all of the sections that talked about quantum theory. And in this video, we're going to go over the electronic structure of atoms. So as mentioned in the previous video, the Schrödinger equation, which allows you to solve for a wave function represents the probability of finding a particle, and we're talking about like a subatomic particle, like an electron, at any position in space, at any point in time. Schrödinger didn't invent the idea of the wave function. He just came up with a way to solve for a wave function in general 3D space. Now, the general idea is, if you think about a multi-electron atom, you use the Schrödinger equation to solve for the wave function of each individual electron. Each individual electron is going to have its own wave function that you solve with the Schrödinger equation. It's a differential equation, and you solve the differential equation for the wave function. But the wave function is a general wave function for any circumstance. It's just a general. It's completely general. The Schrödinger equation is for any general situation that you want to find a wave function for some mass. But if you apply it for the case of electrons in an atom, or it could be hydrogen, so it's a one electron atom or a multi-electron atom as well, then to solve the equation, you need to apply boundary conditions. To solve the Schrödinger equation for any situation, the idea is you set up the boundary conditions for that specific situation. And so thinking about for electrons in an atom, you need boundary conditions as well that are unique to the positions of electrons are surrounding an atom. For a general 3D space, for any specific electron, to solve for its wave function in 3D space, general 3D space, you need three boundary conditions. These boundary conditions are called the quantum numbers. That's why each electron is going to have three quantum numbers associated with it. And those quantum numbers result in that electron's wave function, which describes the electron's position in space. It's also its energy, because you can take a derivative of a position function and get a velocity function. It gives you all the information about the electron, its position, its energy, right? So with this, you can get the electron configurations, because you can solve the wave equation for each electron in a multi-electron atom. And you might be wondering, well, in a multi-electron atom, don't the electrons interact with one another? Yes, and in the video, the quantum theory video, the full-length video, I talk about how they deal with that. It's not as complicated as you would think it is. Okay, but these are called quantum numbers because it's exactly what it sounds like. It's only these specific values. Like the principal quantum number, it's going to be a value from it's going to be 1, 2, 3, and so forth. The angular momentum quantum number, it's going to be some integer value. Doesn't have to be an integer, but it's just the idea of quantum, only specific numbers. You're constrained to only a finite number of positions. Okay, so again, each electron is going to have its own principal quantum number, magnetic quantum number, or angular momentum quantum number, magnetic quantum number, and those are the boundary conditions that result in the wave function for that electron. Now, there is a fourth quantum number, but this doesn't have anything to do with the Schrödinger equation. It doesn't have anything to do with the electron configuration. We'll talk about that in a second. Okay, so the first quantum number is the principal quantum number. This number can have integral values 1, 2, 3, and so forth. So from 1 to, not infinity, but 1, 2, 3, 4, 5, 6, and so forth. It corresponds to the quantum number in equation 7.5. This equation was this was the energy state, the energy states of electrons in the hydrogen atom. So it gave the energy level, it gave all of the energy levels. Equation 7.5, the variable was like En. E is a function of the integers, and it gave the energy levels at the for the different orbitals of the electron in the hydrogen atom. And in general, that's how you can think about the meaning of the principal quantum number. It's giving you the energy level of that electron. In general, you can think about it that way. And in fact, for the hydrogen atom, that's exactly what N represents. But we're going to see in a little bit that this is not exactly the case for many electron atoms. There are some variations that we're going to talk about. But again, in general, you can think about the principal quantum number this way. The principal quantum number also relates to the average distance of the electron from the nucleus in a particular orbital. The larger n is, the greater the average distance of an electron in the orbital from the nucleus, and therefore the larger the orbital. You can also think about the principal quantum number that way. And there are no exceptions here as far like there is with energy. Even for multi-electron atoms, the larger the quantum number, the larger the average distance of the electron from the nucleus. No matter, in general, that's the case for for any atom, and therefore the larger the orbital. All right, next quantum number, the angular momentum quantum number. This was N, this is L. The angular momentum quantum number tells us the shape of the orbital. The values of L depend on the value of the principal quantum number N. For a given value of N, L has possible integral values from 0 to N minus 1. So if N is equal to 1, there's only one possible value of L. That's L is equal to 0. If N is equal to 2, there are two values of L, given by 0 and 1. If N is equal to 3, there are three values of L, given by 0, 1, and 2. So here, again, this is telling you the shape of the orbital, and each energy level or each principal quantum number has a certain number of L values associated with it. That's what they're saying. And those go from the possible L values for any given N value goes from 0 to N minus 1. So when N is equal to 1, all you've got is 0 because you go from 0 to 0. So the only L value that corresponds to N is equal to 1 is 0. For N is equal to 2, at the second principal quantum number, the possible values of L are 0 to N minus 1, 2 minus 1 is 1. So 0 and 1 are the L values associated with N is equal to 2, and so on. Okay, the value of L is generally designated by the letters S, P, D, etc. as follows. So these L values are designated, associated with these. You can also say that the 0 L value, you call that, you say that's the S, it's call it S. The L value of 1, you call that P. This also represents the shape of the orbital. If you have an L value of 0, then you think a certain shape, but that shape you're thinking of is the shape of an S orbital. So for example, if L is equal to 0, then you're talking about an S orbital, because remember, the L value is talking about the shape of the orbital. If L is equal to 1, you're talking about a p orbital shape. All right. The unusual sequence of letters S, P, and D has a historical origin. Physicists who studied atomic emission spectra tried to correlate the observed spectral lines with the particular energy states involved in the transitions. They noted that some of the lines were sharp, some were rather spread out or diffuse, and some were very strong and hence referred to as principal lines. Subsequently, the initial letters of each adjective were assigned to those energy states. However, after the letter D and starting with the letter F for fundamental, the orbital designations follow alphabetical order. So that's interesting. Okay, a collection of orbitals with the same value of N is frequently called a shell. So you have they're talking about the principal quantum number, N, the energy level. Each energy level is frequently called a shell. Okay, one or more orbitals. So now we're talking about the orbitals. This was a collection of orbitals. That's called a shell. A collection of orbitals is called a shell because N can have different orbitals, right? N can have different multiple L values. So a collection of orbitals with the same N is called a shell. One or more orbitals, so now we're talking not collection of orbitals, but just orbitals with the same N and L values are referred to as a subshell. So like the S subshell, or no, it would be the 2S subshell or the 3P subshell, for example. All right, the magnetic quantum number. The magnetic quantum number, M sub L, describes the orientation of the orbital in space. So the orientation of the orbital, not the shape of the orbital, the orientation of the orbital. Within a subshell, the value of M sub L depends on the value of the angular momentum quantum number L. Okay, so within a subshell, right? So the same principal quantum number and the same L, the value of ML depends on the value of the angular momentum quantum number L. So it just depends on L, not on N. For a certain value of L, there are two L plus 1 integral values of M sub L as follows. So for any value of L, again, this does not depend on N. Within a subshell, so a certain value of N and a certain value of L, the M sub L values depend on just the value of the angular momentum quantum number L. So for a certain value of L, there are two L plus 1 integral values of M sub L as follows. So you take L, you're in a certain subshell, you take L, and then you find 2 times L plus 1. So let's say you have L is equal to 0. Then the value would be 1. If you have L is equal to 2, the value would be, or if you have L is equal to 1, the value would be 3. If L is equal to 2, the value would be 5. Then the possible M sub L values are, you're centered around 0. So if L is equal to 0, that means you have just 1, then you have 1 M sub L value. It's going to be 0. If L is equal to 1, so 2L plus 1 is 3, then you have 3 M sub L values minus 1, 0, 1. If L is equal to 2, then you have 2 times 2 is 4 plus 1 is 5. 5 M sub L values, which are minus 2, minus 1, 0, 1, and 2. And again, these just represent the orientation of that orbital. The L value is giving you the shape, the N value, the energy level, or the average distance from the nucleus. And then the M sub L is telling you the orientation of that orbital shape. Okay, so with those 3 quantum numbers, now you've constrained an electron to an energy level in a position in space around the nucleus. You know its energy level, you know its the size of the orbital, you know the shape of the orbital, and you know the orientation of the orbital. But there is a 4th quantum number. So this is the electron spin quantum number M sub S. It says experiments on the emission spectra of hydrogen and sodium atoms indicated that lines in the emission spectra could be split by the application of an external magnetic field. The only way physicists could explain these results was to assume that electrons act like tiny magnets. If electrons are thought of as spinning on their own axes, as Earth does, their magnetic properties can be accounted for. According to electromagnetic theory, a spinning charge generates a magnetic field, and it is this motion that causes an electron to behave like a magnet. Figure 7.16 shows the 2 possible spinning motions of an electron, one clockwise and the other counterclockwise. To take the electron spin into account, it is necessary to introduce a 4th quantum number, called the electron spin quantum number M sub S, which has a value of plus 1/2 or minus 1/2. So again, the emission spectra of the hydrogen and sodium atoms indicated that the lines could be split by the application of an external magnetic field. And the only way they could explain this was by thinking about the electron as spinning. And they know that spinning charge produces a magnetic field, right? Because they need to be able to predict the emission spectrum with this electron configuration model. That's important. And so when they found this, they had to say, well, look, we need to come up with another constraint so we can predict any emission spectrum accurately. So that's what the electron spin came from. And they're not just arbitrarily coming up with some random idea to solve these problems, because the theory they come up with is verified by experiments. So it says here, conclusive proof of electron spin was provided by Otto Stern and Walter Gerlach in 1924. Figure 7.17 shows the basic experimental arrangement. A beam of gaseous atoms generated in a hot furnace passes through a non-homogeneous magnetic field. The interaction between an electron and the magnetic field causes the atom to be deflected from its straight line path. Because the spinning motion is completely random, the electrons in half of the atoms will be spinning in one direction, and those atoms will be deflected in one way. The electrons in the other half of the atoms will be spinning in the opposite direction, and those atoms will be deflected in the other direction. Thus, 2 spots of equal intensity are observed on the detecting screen. So if we look here, you have this hot oven, so you have these gaseous atoms coming out. They go through this magnetic field here, and you get these 2 sharp points, 2 distinct points on the detecting screen. So it's this magnetic field interacting with what can only be explained as the spin of the electron, because there's only 2 possibilities. It's one direction of spin and another direction of spin. It's these 2 distinct points here. It's not like there's some other factor going on. So you have you have more than 2 hotspots on the detecting screen. See? Okay, table 7.2 shows the relation between quantum numbers and atomic orbitals. We see that when L is equal to 0, 2L plus 1 is equal to 1, and there is only one value of ML. Thus, we have an S orbital. When L is equal to 1, 2L plus 1 is equal to 3, so there are 3 values of ML, or 3 p orbitals, labeled px, py, and pz. When L is equal to 2, 2L plus 1 is equal to 5, and there are 5 values of ML. And the corresponding 5 d orbitals are labeled with more elaborate subscripts. So now we're going to take a closer look at the s, p, and d orbitals to get a sense for orbitals. But if we look in this table here, they're saying, so n is equal to 1, which means there's only L is equal to 0. When n is equal to 2, you have 2 minus 1 is 1, so you have 0 and 1. When n is equal to 3, you have 3 minus 1 is 2, so you have 0, 1, and 2 for L. That's the whole shells. Now, if we look at the subshells, for L is equal to 0, we just have ML is equal to 0. So for any subshell where L is equal to 0, the only ML you have is 0. For a subshell where L is equal to 1, you have ML is equal to minus 0, minus 1, 0, and 1. For 2, you have minus 2, 1, 0, 1, 2. There's 5 values of ML, 2L plus 1. And so when you have a subshell where L is equal to 1, you've got these 3 p orbitals, px, py, pz. Here's the subshell. N is equal to 2, L is equal to 1, 2 px, 2 py, 2 pz. Here's the subshell where N is equal to 3, L is equal to 1, 3 px, 3 py, 3 pz. And then for it's not a D subshell. Remember, a subshell is talking about, it corresponds to a certain value of N and a certain value of L. So this is the 3D subshell, but you can see the subscripts they use for the D subshell. dxy, dyz, dxz, dx squared minus y squared, dz squared. And we'll get a sense for what these subscripts mean in a second. So the s orbital. One of the important questions we ask when studying the properties of atomic orbitals. Okay, so remember, we're talking about orbitals. Orbitals have a shape and an orientation. The shape of the orbital is given by L, the orientation by m sub L. So one of the properties we ask when studying atomic orbitals is, what are the shapes of the orbitals? Strictly speaking, an orbital does not have a well-defined shape because the wave function characterizing the orbitals extends from the nucleus to infinity. In that sense, it is difficult to say what an orbital exactly looks like. On the other hand, it is certainly convenient to think of orbitals as having specific shapes, particularly in discussing the formation of chemical bonds between atoms, as we will do in chapters 9 and 10. Although in principle, an electron can be found anywhere in space, we know that most of the time it is quite close to the nucleus. Figure 7.18 shows the distribution of electron density in a hydrogen 1s orbital moving outward from the nucleus. Okay, so if we look here, just in general, we can see that the distribution of the electron probability density going outward from the nucleus. But like they said, technically, this probability density extends to infinity. There's still a probability all the way out here that the electron could be here. As you can see, the electron density falls off rapidly as the distance from the nucleus increases. Roughly speaking, there is about a 90% probability of finding the electron within a sphere of radius 100 picometers surrounding the nucleus. Thus, we can represent the 1s orbital by drawing a boundary surface diagram that encloses about 90% of the total electron density in an orbital, as shown in figure 7.18b. A 1s orbital represented in this manner is merely a sphere. So if we come here, what they're saying is, what we're going to do for any orbital, not just the s orbital, is draw a boundary surface that to where everything inside of that boundary surface, there's 90% of the probability of finding the electron within that boundary surface. And that's how we can get a vision for the shape of the orbital. Here they do that here, but if you think about this in 3D, this is a sphere. And again, we're going to use the same idea to visualize p orbitals and d orbitals, etc. Everything inside of the boundary surface, it doesn't have to be spherical, it would mean that there's a 90% probability of finding the electron within that surface. Okay, and here we can look at C here. This is a more realistic way of viewing electron density distribution is to divide the orbital into successive spherical thin shells. A plot of the probability of finding the electron in each shell, called radial probability, as a function of distance, shows a minimum of 52.9 picometers from the nucleus. Okay, so yeah, what they're showing here is just to get a sense of the probability distribution. You might think that, so inside this boundary surface, there's a 90% probability of finding the electron. And if you imagine drawing more boundary surfaces with different radiuses, it would just be, like a linear function, like it would, or a volumetric function, or just some even distribution, right? As the radius gets a little bit bigger, you get a little bit more probability, but that's not necessarily the case. If you'd have to go into quantum mechanics to get the specifics, but like what they're showing here is the probability, the total probability density inside of each of these spheres. This is how it's distributed. So the probability goes up a lot, like right when you're coming away from the nucleus. It shoots up a good bit fast. Then the larger the radius of the boundary surface, it doesn't go up as much. This is the distribution, right? So if you're really close to the nucleus, then the probability is not that high because the electron's going to be some distance away from the nucleus. But if you start drawing a boundary surface just away from the nucleus, the probability goes up fast. But then as you keep drawing boundary surfaces, the probability density doesn't increase as fast. Figure 7.19 shows boundary surface diagrams for the 1s, 2s, and 3s hydrogen atomic orbitals. All s orbitals are spherical in shape but differ in size, which increases as the principal quantum number increases. Although the details of electron density variation within each boundary surface are lost, there is no serious disadvantage, right? So like we were just talking about, if you studied quantum mechanics, it's not just a simple, the details of the electron density variation within each boundary surface, we don't technically learn that in general chemistry, right? If we come back here, that's what I'm talking about here. It's not just necessarily some linear distribution of electron density within the boundary surface, the 90% boundary surface. You have to look at it specifically. Could be something like this. But although we don't see that in general chemistry, we're not aware of that in general chemistry, it says it's not a serious disadvantage. For us, the most important features of atomic orbitals are their shapes and relative sizes, which are adequately represented by boundary surface diagrams. Yeah. Their shapes and their relative sizes, that's what we need to be aware of in general chemistry. The shape, relative size between the different orbitals, the 1s, 2s, 3s, the 2s and 2p, etc., 1s and 3d, how their shapes and sizes differ. And we can get a sense of that size with a 90% boundary surface. And the actual distribution, just be aware that it's not necessarily this like a linear distribution. All right, p orbitals. It should be clear that the p orbitals start with the principal quantum number n is equal to 2. And the reason is because what you do is you take the principal quantum number, subtract 1, and that gives you the possible values of L. If you have n is equal to 1, 1 minus 1 is 0. The possible values of L are just 0. N is equal to 2. Subtract 1, you have 1 from 2, you have 1. The possible values of L are 0 and 1. P orbital corresponds to L is equal to 1. Okay, as we saw earlier, when L is equal to 1, the magnetic quantum number ML can have what values? You take 2 times L plus 1, you get 3. Okay, so there's 3 total M sub L's, which means you do minus 1, 0, and 1. That gives the different orientations of the p orbital. Okay, so starting with n is equal to 2 and L is equal to 1, we therefore have 3 2p orbitals, 2px, 2py, and 2pz. Okay, so here's 2px, 2py, and 2pz. And we can get a sense of what they mean by this, the orientation. Here, it's oriented along the x direction, here along the y, and here along the z. And it's not a sphere, it's like these two lobes. Those lobes aren't spherical. It's kind of like dumbbells. But again, you have L is equal to 1. They're all p orbitals, but then there's 3 different orientations because 2L plus 1 is equal to 3. That means there's 3 different orientations given by the quantum numbers minus 1, 0, and 1, the M sub L quantum numbers. These three p orbitals are identical in size, shape, and energy. They differ from one another only in orientation. Note, however, that there is no simple relation between the values of m sub L and the x, y, and z directions. For our purpose, you need only remember that because there are three possible values of m sub L, there are three p orbitals with different orientations. So what they're saying here is that you can't say, okay, m sub L is minus 1, 0, and 1, so minus 1 must be the p sub x, and 0 must be the p sub y, and 1 must be the p sub z. It's saying here there's no simple relation between the values of m sub L and which one is in the x, y, and z direction. You just need to, for general chemistry, you just need to remember that there are three possible values of m sub L, and there are three p orbitals with different orientations. And then I guess you could also think about it like these are how the orientations differ. They're kind of perpendicular to one another. I mean, that's still a fact. You just don't know which is which. You can't say, oh, this is the minus 1 m sub L. The boundary surface diagrams of p orbitals in figure 7.20 show that each p orbital can be thought of as two lobes on opposite sides of the nucleus. Like s orbitals, p orbitals increase in size from 2p to 3p to 4p orbital and so on, right? So again, if the principal quantum number is definitely directly related to the average distance from the nucleus. The higher the principal quantum number, the larger that 90% boundary surface is going to be. But it's not necessarily the case that the higher the larger the n, the larger the larger the energy is going to be. In the next section, we'll get more specifics on that. For the hydrogen atom, that is the case. The larger the n, the higher the energy of the orbital. But for larger electron atoms, that's not, in general, that is the case, but it's not a hard and fast rule. There's certain cases where it doesn't work that way. Okay, but same idea though. If we look here, this is like a 90% surface, boundary surface. 90% of the electron probability density is contained within this surface. And another thing that can be kind of confusing is, remember that these two lobes taken together represent one orbital. So the electron might be on this side, it might be on this side. This is still all one orbital. It's not two separate orbitals joined together. This is one p orbital. Okay, d orbitals and other higher energy orbitals. When L is equal to 2, 2L plus 1 is equal to 5. So the orientation quantum numbers are minus 2, minus 1, 0, 1, 2. That's 5. So there are 5 values of m sub L, which correspond to 5 d orbitals. The lowest value of n for a d orbital is 3. Why is that? Because the L value for a d orbital is when L is equal to 2. Remember, the L value specifies the orbital. Is it S, P, D, F? So you have to have at least an n value equal to 3. Because when n is equal to 3, you take n minus 1, 2. So the orbitals for n is equal to 3 are 0, 1, and 2. But there's also d orbitals when you say like n is equal to 4, because 4 minus 1 is 3. So for n is equal to 4, you'll have 0, 1, 2, 3. You still have L is equal to 2. Okay, but when L is equal to 2, 2L plus 1 is equal to 5. So there's 5 d orbitals at 5 different orientations, shown in figure 7.21. Let's go take a look at figure 7.21. This is what the d orbitals look like. And the subscripts correspond to these shapes. You can do your own research to see exactly what these subscripts, how these subscripts correspond to the shapes, or to the orientations, not the shapes, to the orientations, sorry. Well, and also potentially the shapes as well. This is its own distinct shape compared to the other ones. But again, you can do your own research on this, on those orientation subscripts. As mentioned, the only thing you need to be concerned about is that there are 5 different d orbitals, and this is what they look like. And then if the larger the principal quantum number corresponding to that d orbital, the shape is exactly the same. It's going to be the size of that 90% boundary surface is going to be larger. But this is the different shapes and orientations. Okay, as is in the case of the p orbitals, the different orientations of the d orbitals correspond to different values of m sub L. But again, there's no direct correspondence between a given orientation and a particular m sub L value. So we don't know, we can't say this is the m sub L value that's equal to 0 or minus or 1 or minus 1. But we don't need to be concerned about that. All the 3D orbitals in an atom are identical in energy. Okay, so That's also something to note. I don't know if I mentioned that when we were talking about the p orbitals or the s orbitals. All of the orbitals within a specific subshell. So remember, a shell corresponds to a quantum number. It's a collection of orbitals. So the n is equal to 2 shell, or the n is equal to 3 shell. Of course, it's those collection of orbitals. Those aren't necessarily all the same energy, because they have the same principal quantum number. And we're going to see why that is in a second. That's only the case for the hydrogen atom. That's the case. For multi-electron atoms, that's not the case. However, for all the orbitals within a subshell, so a subshell, remember, it's a certain principal quantum number and a certain L value. So like the 3p subshell, the 4d subshell, all of the orbitals within the same subshell have the same energy. Okay, so that's important. Remember that. Okay, the d orbitals for which n is greater than 3 have similar shapes. So as the principal quantum number increases, the average distance of the electron from the nucleus increases, but the shapes of the orbitals don't change. Orbitals having higher energy than d orbitals are labeled F, G, and so on. The F orbitals are important in accounting for the behavior of elements with atomic numbers greater than 57, but their shapes are difficult to represent. In general chemistry, we are not concerned with orbitals having L values greater than 3, so like the G orbitals and beyond. We don't even have, we're getting to areas where we haven't even discovered elements that have that many electrons, that have that large of atomic numbers, because the number of protons corresponds to the number of electrons. But so in general chemistry, we're not really going to be going past the L value greater than 3. So past the F orbital. But there are G orbitals you can think about, and potentially beyond. Okay, so now let's talk about the energies of orbitals. I've touched on this a little bit, but in general, when you think about the energy of an orbital, you do look at the principal quantum number. In general, it's true that the larger the principal quantum number, the larger the energy. That is true. And in fact, it shows here that when you look at the hydrogen atom, it is literally the case that to get the energy of an orbital, or to compare the energies of orbitals, you just reference the principal quantum number. So 2s is equal to 2p in energy, which is greater than 1s. 3s is equal to 3p is equal to 3d in terms of energy, which is greater than anything with a principal quantum number of 2. Okay, like shown here. Same principal quantum number, same energy. The larger the principal quantum number, the larger the energy. And you can also get a sense of, this is just for the hydrogen atom, how it's not an even distribution either. It's not like it goes, when you go from 1s to 2, when you go from 1 to 2, it's the same jump in energy as going from 2 to 3 and 3 to 4. It's nonlinear, right? Okay, so although the electron density distributions are different in the 2s and 2p orbitals, hydrogen's electron has the same energy whether it's in the 2s orbital or a 2p orbital. The 1s orbital in a hydrogen atom corresponds to the most stable condition, the ground state. An electron residing in this orbital is most strongly held by the nucleus because it is closest to the nucleus. An electron in the 2s, 2p, or higher orbitals in a hydrogen atom is called an excited state. Is in an excited state. All right. The energy picture is more complex for many electron atoms than for hydrogen. The energy of an electron in such an atom depends on its angular momentum quantum number as well as on its principal quantum number. Okay, so it depends on the energy of a multi-electron orbital. The energy of an orbital in a multi-electron atom depends on both the principal quantum number and the angular momentum quantum number. For many electron atoms, the 3D energy level is very close to the 4s energy level. The total energy of an atom, however, depends not only on the sum of the orbital energies, but also on the energy of repulsion between the electrons in these orbitals. Each orbital can accommodate up to 2 electrons, as we will see in section 7.8. It turns out that the total energy of an atom is lower when the 4s subshell is filled before a 3D subshell. So it's just saying that you have to account for the orbitals have different shapes, and then because they have different shapes, you're also accounting for the energy of repulsion between electrons. And then these orbitals have different shapes, so you can have different levels of repulsion between different orbital shapes. So that's why the angular momentum quantum number, the orbital shape quantum number comes into play. And so they show here we go from, this is for a multi-electron atom. This is for any multi-electron atom. So it's not just certain, it's not like certain multi-electron atoms have different orbital energy distributions. Like you don't have to say, well, if I'm dealing with a metal, this certain type of metal, it's going to have this energy distribution of orbitals compared to this other metal. So it's nice that it's the only reason the hydrogen atom doesn't have this distribution here, this energy distribution, is because it's one electron. So what you're filling up for every orbit, like the electron in the hydrogen atom can, depending on how how much it's heated or whatever, that electron can be in these different orbitals, but there's no other electrons there for it to interact with. So it just follows this simple pattern of just being related to the principal quantum number. For multi-electron atoms, there's always that at least one electron that's there for it to interact with. So it follows a pattern like this. You go 1s, 2s, 2p, 3s, 3p. So even within the same shell, it's not like 2s and 2p or have equal energies. You go from 1s to 2s and then just going to 2p, you're still within the same shell, you go up in energy. 3s, 3p. Now you go 4s, 3d, 4p, 5s, 4d. And you might be saying, well, how am I going to remember this? You get used to drawing a chart like this. This is the best way to memorize it. So memorize this layout here. I would really strongly suggest you memorize this layout. Put 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. Then you would do 6s, 6p, 6d, 6f if you would extend this out. 7s, 7p, 7d, 7f, and you could put g if you wanted to. Right? Where would you put G? You'd put G here. And then you would have 6D, 6F, 6G, and then, if you want to keep going, you'd put 6H, but, you wouldn't even put the G. But and the idea is you fill it up. You go 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S. And so if you just memorize this, and then you'll know the energy levels. And it's important to know for actually doing the actual electron configuration, which we'll do in the next section. You need to know which to fill up first. You need to know these energy levels distribution. So again, memorize how to write out this chart and put the arrows and go through and walk through the increasing energy levels of the orbitals. Okay, electron configuration. The four quantum numbers NL, M sub L, and M sub S enable us to label completely an electron in any orbital in any atom. In a sense, we can regard the set of four quantum numbers as the address of an electron in an atom, somewhat in the same way that a street address, city, state, and postal zip code specify the address of an individual. For example, the four quantum numbers for a 2s orbital electron are n is equal to 2, L is equal to 0, M sub L is equal to 0, and M sub S is equal to plus or minus 1/2. It is inconvenient to write out all the individual quantum numbers, and so we use the simplified notation. You put a parentheses and then list out with commas the four quantum numbers. For the preceding example, the quantum numbers are either 2, 0, 0 plus 1/2 or 2, 0, 0 minus 1/2. The value of M sub S has no effect on the energy, size, shape, or orientation of an orbital, but it determines how electrons are arranged in an orbital. Okay. The hydrogen atom is a particularly simple system because it contains only one electron. The electron may reside in the 1s orbital, the ground state, or it may be found in some higher energy orbital, which would put it in an excited state. So just note that. Don't get so used to, when you think about electron configurations, just thinking about the ground state of an atom. So like for the hydrogen atom, yes, in general, if you're just looking at a periodic table and you see the hydrogen atom, you think you have that one electron in the 1s orbital. But that electron can jump to an excited state, to theoretically any higher energy orbital. and then it jumps back down to a lower energy orbital, and then it will give off an electromagnetic ray. It can go to an excited state, and the electron doesn't have to jump back down to the ground state. The electron could go it could jump to a 3p orbital and then jump back down to a 2s orbital, and it'll give off a certain electromagnetic wave. And same idea when we're about to talk about multi-electron atoms. Yeah, you have the ground state, but those electrons can jump to all kinds of excited states. Okay, but for many electron atoms, we must know the electron configuration of the atom, right? So hydrogen has one electron, and that electron can theoretically go anywhere when it's excited. But for multi-electron atoms, we first need to think about the ground state and think about the electron configuration of the ground state. And then for excited states, you have to, imagine, well, an electron might want to jump to an excited state, but it can't because there's already an electron above it or occupying other excited states. So you have to think about it that way. You have to think about the electrons interacting together for multi-electron atoms. And so in general, even hydrogen has an electron configuration, but for multi-electron atoms, for all atoms in general, we must know the electron configuration of the atom. That is, how the electrons are distributed among the various atomic orbitals. In order to understand electronic behavior, we will use the first 10 elements, hydrogen to neon, to illustrate the rules for writing electron configurations for atoms in the ground state. And then in the next section, we'll talk about electron configurations for atoms with more than 10 electrons. For this discussion, recall that the number of electrons in an atom is equal to its atomic number, Z. Figure 7.22 indicates that the electron in a ground state hydrogen atom must be in the 1s orbital, so its electron configuration is 1s1. So we're starting with hydrogen. This is hydrogen's electron configuration, 1s1. You see the principal quantum number, the orbital, and then this denotes the number of electrons in that orbital. The electron configuration can also be represented by an orbital diagram that shows the spin of the electron. So this is an electron configuration, and we'll see larger electron configurations as we go. This is the electron configuration, but represented with an orbital diagram as well. And so this is like the orbital, and you indicate that there's that one electron in the orbital. And then you put the orbital the orbital below. We know that this is the 1s orbital. And technically, you don't need for this. You don't technically you don't need the superscript 1 here because you show that this is the 1s orbital and has that one electron in it. But you're still going to put the superscript because you're putting the electron configuration. This shows the electron configuration in addition to this orbital diagram. The upward arrow denotes one of the two possible spinning motions of the electron. Alternatively, we could have represented the electron with a downward arrow. The box represents an atomic orbital. All right, so that's hydrogen. Now, to move forward, we need to understand, this is a principle we need to understand, the Pauli Exclusion Principle. For many electron atoms, we use the Pauli Exclusion Principle to determine electron configurations. This principle states that no two electrons in an atom can have the same set of 4 quantum numbers. Okay, so this is, again, this is going to, so you can know exactly how to make electron configurations for multi-electron atoms. This is an important rule here. You cannot have 2 electrons that have the same 4 quantum numbers. That's you can't do that. That violates the rules of quantum mechanics. If 2 electrons in an atom should have the same NL and ML values, that is, these 2 electrons are in the same atomic orbital, right? They're saying if you have a certain NL and ML, then you're specifying a specific orbital. Right? That's now you're talking about a certain orbital. Okay? If you have an NL and ML value, you've picked an NL and an ML, M sub L. Then that means that you like the 2 electrons that have the same, or 2 or more electrons that have the same NL and M sub L values, they must have the different M sub S's. However, there's only 2 possible M sub S's, which means that only 2 electrons can occupy the same atomic orbital. If for some reason the experiments and the evidence showed that there was, different types of spins, right? There was, when we talked about that experiment that showed that there was only 2 potential spins of the electron in just clockwise or counterclockwise, there were only 2 hot spots on the detecting screen, maybe there was 4 hot spots for some reason. So like you have like it was a counterclockwise spin, a clockwise spin, then also maybe like a perpendicular spin to that, right? You could potentially spin like this, but maybe you could also spin like this. Let's say there was evidence that showed that there was 4 different spinning states instead of 2. Then for the same orbital, if you had the same N, L, and M sub L values, you could have 4 different M sub S's, and that would mean that 4 electrons could occupy the same orbital, but that's not the case. Only 2 electrons can occupy the same atomic orbital. That's because of the Pauli Exclusion Principle. As a result of the Pauli Exclusion Principle, only 2 electrons can occupy one atomic orbital. There can be 1 in an atomic orbital, there can be nothing in an atomic orbital, and there can be 2 in an atomic orbital, and that's it. If you have no electrons in an atomic orbital, 1 electron in an atomic orbital, or 2, for all 3 of those scenarios, you haven't violated the Pauli Exclusion Principle. But to have 3 electrons or more, then you'll be violating the Pauli Exclusion Principle. Well, and then furthermore, if you do have 2 electrons in the same orbital, those electrons must have opposite spins to not violate the principle. Consider the helium atom, which has 2 electrons. The 3 possible ways of placing 2 electrons in the 1s orbital are as follows. There's only 3 possible ways. These 2 ways violate the Pauli Exclusion Principle. Only this way does not. So that's how, if you have, from the standpoint of an orbital diagram, which you can see the electron configuration notation doesn't specify the spins at all. But with the orbital diagram, you can see the spins, and this is the only way you can put 2 electrons in in a single atomic orbital. You can't put 3. You could put 1, none, or 2. And if you do put 2, you have to put it like this with opposite spins. So there's the helium electron configuration. And it's read as, this is 1s2, not 1s squared. You read it as 1s2. Okay, diamagnetism and paramagnetism. The Pauli Exclusion Principle is one of the fundamental principles of quantum mechanics. It can be tested by a simple observation. So how could you potentially experimentally verify the Pauli Exclusion Principle? If the 2 electrons in the 1s orbital of a helium atom had the same or parallel spins, their net magnetic fields would reinforce each other. Remember, the spins is related to it's related to magnetism, because you've got the spin of the electron, and that we know that a moving charge or a spinning charge generates a magnetic field. Okay, but if you had parallel spins, this arrangement would make the helium gas paramagnetic. Paramagnetic substances are those that contain net unpaired spins and are attracted by a magnet. So this is interesting. This is giving you a sense of where permanent magnets come from. So yeah, you can have like a electric motor where you have a coil and you run a current through it, and that generates a magnetic field and spins a shaft. But what about permanent magnets? Right? Like you have a magnet, people back in the centuries ago would find these rocks that were attracted to each other with these large forces, pretty large. Where do those come from? You're not running a current through those. This is showing you. It's these parallel spins or net unpaired spins. And you'll see what that means in a second. Okay. On the other hand, if the electron spins are paired or are anti-parallel, and they're saying paired because the only way to pair, we just saw the only way to pair 2 electrons together is their electron spins are opposite. You can't have 2 paired parallel spins. That violates the Pauli Exclusion Principle. So if they're paired or anti-parallel, which is like shown here, the magnetic effects cancel out. And so you don't have, the material's not magnetic. Diamagnetic substances do not contain net unpaired spins and are slightly repelled by a magnet. So this is kind of confusing because you would think diamagnetic substances aren't magnetic. So this seems to be suggesting that even substances that aren't magnetic, that we would say aren't magnetic, would still slightly repel a magnet. That seems to be what this is suggesting, because you either have substances that don't have net unpaired spins or substances that do. It's either one or the other. And so this seems to be suggesting that even things that are completely known to be non-magnetic still could slightly repel a magnet. I'll look into this further and pin a comment once I get some more information. If anyone, someone that's an expert in chemistry can drop a comment on this, please do. Measurements of magnetic properties provide the most direct evidence for specific electron configurations of elements. Advances in instrument design during the last 30 years or so enable us to determine the number of unpaired electrons in an atom. Right? So here's a general schematic. You've got a magnet, a paramagnetic substance, just like a magnetic substance, right? There's no voltage being applied here. This is just the substance and an electromagnet, and you get it generates a force. This gets pulled down by the magnet, which pulls up the weight. By experiment, we find that the helium atom in its ground state has no net magnetic field, right? Because helium had no net unpaired spins, but then so helium is diamagnetic. Is that what they're saying? Yeah, helium is diamagnetic, but apparently diamagnetic substances slightly repel a magnet, or slightly repelled by a magnet. A useful rule to keep in mind is that any atom with an odd number of electrons will always contain one or more unpaired spins because we need an even number of electrons for complete pairing. On the other hand, atoms containing an even number of electrons may or may not contain unpaired spins. We will see the reason for this behavior shortly. So yeah, you might be saying, so if you have an odd number of electrons, you have a magnetic material, like a magnet on my refrigerator type thing? Well, no, we're going to see how even for potentially even numbered atomic number atoms, you can have more than just one unpaired electron. You can have a bunch, and those are going to be the most magnetic materials. The most magnetic materials aren't going to have just one unpaired spin. And also, I want to say that for they can use manufacturing processes to really increase the magnetic properties. You might have a material that's naturally magnetic based on its electron configuration, but you can do things to make it even more of a stronger magnet by the way you process it, like lining up the crystal structures to where everything's parallel, so you even have even more of a tendency for you strengthen the magnet even more. Okay, so if you have an odd number of electrons or an odd atomic number, we're thinking about the ground state, you're going to have at least one unpaired electron. So you're going to have one, which is like a parallel spin. If we look here, you're going to have a magnetic field coming from this because there's no other electron canceling out the magnetic field. So if you have an odd number of electrons, you're going to have at least one unpaired spin, one or potentially more. And we'll see how you can have more soon. And if there's an even number of electrons, that doesn't mean there's going to be no unpaired spins. You could potentially have unpaired spins, and that's what we're about to talk about. You can have odd numbers of electrons and even have more than one unpaired spin. Same with even. As another example, consider the lithium atom, where Z is equal to 3, your atomic number is equal to 3, which has 3 electrons. The third electron cannot go into the 1s orbital because it would inevitably have the same set of 4 quantum numbers as one of the first 2 electrons, right? Okay, yeah, so we apply the Pauli Exclusion Principle, and we see that, therefore, this electron enters the next energetically higher orbital. You're using the Pauli Exclusion Principle, but then you're also going for the lowest energy state that's free. We're talking about the ground state. So you wouldn't go to the 2p orbital because we're going to talk about soon that p orbitals have higher energy than s orbitals. And you wouldn't go to the 3s orbital because in general that the larger the quantum number, the higher the energy, but not every time because of the we saw that rule, that diagonal chart rule, but looking here, yes, the 3s orbital has a higher energy than the 2s orbital, and also the 2p orbital has a higher energy than the 2s orbital. So this is, of all of the available orbitals, the 2s is the lowest energy. So you put the electron in this orbital, because you can't put an electron here because that violates the Pauli Exclusion Principle. And again, for multi-electron atoms, to know which orbital has the energy, how orbitals increase in energy, what's the order, you use this. That's what this is telling you. So the 4s orbital is lower energy than the 3d orbital. Even though it has a larger principal quantum number, according to this chart, you follow this. You go from here to here to here to here. 4s has a lower energy than 3d. So you would fill this first. Okay, now here we're going to get a sense for the chart we just looked at, the diagonal chart. We're going to get a sense for how we talked about how for multi-electron atoms, the energy of an orbital is a function of the principal quantum number and the angular momentum quantum number, which the L, which specifies if it's a s, p, or d orbital. It specifies the type of orbital. It's a function of both of those quantum numbers. So we're going to get a sense for how the L quantum number, the angular momentum quantum number, factors in. What's going on? Experimentally, we find that the 2s orbital lies at a lower energy level than the 2p orbital in a mini-electron atom. Why? In comparing the electron configurations of 1s2, 2s1, and 1s2, 2p1, so you could potentially have 1s2, 2p1, but this is less energetically favorable. So this is the proper configuration. But we're going to compare these two, and we note that in both cases, the 1s orbital is filled with 2 electrons. Okay, yep. Figure 7.27 shows the radial probability plots for the 1s, 2s, and 2p orbitals. So this is it showed the density cloud, and then we put, you plotted the percentage of the electron probability density inside of the sphere at different radiuses. And that's what this is doing. As you get the distance from the center of the orbital increases, what is the probability density? Well, here it's not inside of the entire sphere, because if that was the case, or inside of the entire orbital, because if that was the case, this density would never come back down. So it's just saying, at least at each specific location, what's the probability density? So you can get a sense for the distribution in that way. Okay, because the 2s and 2p orbitals are larger than the 1s orbital, an electron in either of these orbitals will spend more time away from the nucleus than an electron in the 1s orbital. Yeah, so if the principal quantum number is larger, then the peak of the curve of this curve will be farther to the right every time, right? You see how these peaks, these curves, the peak and the whole curve is shifted to the right. That will always be the case if the principal quantum number is higher, which means that the orbital is larger. Okay, so with this in mind, we can speak of a 2s or 2p electron as being partly shielded from the attractive force of the nucleus by the 1s electrons. Now, this is kind of confusing. It's saying shielded, but if it was unshielded, that would be more stable. Remember that the farther you are an electron is away from the nucleus, the more energy it has, the less stable it is, right? We talked about how it takes, if the orbital is closer to the nucleus, it takes more energy to pull that electron away. So this shielding idea, it's shielding it from stability. It's making it higher energy the more it's shielded. Okay, so both the 2p and the 2s electrons, since they spend time farther away from the nucleus, they're shielded because they are repelled by the 1s electron. The important consequence of the shielding effect is that it reduces the electrostatic attraction between the protons in the nucleus and the electron in the 2s or 2p orbital. That's a stabilizing effect. That's why energies of electrons are negative, and a completely free electron has energy equal to 0. It's a stabilizing effect to have the electron experience that attractive force with the nucleus. And why is that? The basic concept of energy, because it takes energy to take it out of that attraction. To move it away, it takes energy. And if you wanted to bring the electron back, it wouldn't take energy to put it back into an orbital. Imagine if you you were holding an electron, you brought it back towards the atom. Once it got close, you just let go and it snaps into place. But then to take it out, it takes energy. So the more their electrostatic attraction there is between the proton and electron, the lower the energy of the electron between the nucleus and the electron. And so that's the idea of this shielding. Electrons that have lower principal quantum numbers, or electrons that are in smaller orbitals, shield electrons in larger orbitals from the attractive force of the nucleus. They do this because like charges repel. That electron wants to move, outer electron wants to potentially move closer to the nucleus, but it's repelled by the inner electron. Okay, now you look here, if we look at the 2p and the 2s, you would think, well, it looks like the 2p is a lower energy state than the 2s, right? The 2s is further out, right? The 2s seems as though the 2s electron spends more time or more amount of time away from the nucleus than does the 2p. So it's lower energy, or it's higher energy. Well, let's take a look here. The manner in which the electron density varies as we move from the nucleus outward depends on the type of orbital. The manner in which the electron density varies as we move from the nucleus depends on the type of orbital. Yeah, so these curves here are going to depend on the type of orbital. Although a 2s electron spends most of its time on average slightly farther from the nucleus than a 2p electron, the electron density near the nucleus is actually greater for the 2s electron because of this piece here. It does spend more time on, if you averaged out the distance from the nucleus, the 2s electron does spend more time farther away from the nucleus, but it has this peak here, causes the electron density near the nucleus to be greater for the 2s electron. So I guess you can think about it as at closer distances, the volume is smaller. For this reason, the 2s orbital is said to be more penetrating than the 2p orbital. Therefore, a 2s electron is less shielded by the 1s electrons and is more strongly held by the nucleus. So again, this is kind of confusing, but even though this seems to be farther away from the nucleus, or it is, this is a larger orbital, there's still less shielding of the 2s electron from the nucleus by the 1s electron than there is the 2p because of this here. So this has a more penetrating power, the s orbital. And so this extra penetrating power of the orbital, it isn't enough to make like the 2s orbital less stable than the 3p orbital, let's say, right? Because even though the s orbital is more penetrating than the p orbital, you still have that principal quantum number that moves the 3p orbital further away, right? The 3p orbital might be out here, right? And so it doesn't matter that the s orbital is more penetrating than the p orbital. This is going to be more stable, the 2s, than the 3p. Why? Because the 3p is larger than the 2s. But here, because the principal quantum numbers are the same, the 2p is smaller than the 2s, but the 2s still can overcome that because of its additional penetrating power. So the 2s is still more stable than the 2p. Okay, and so that's why, if we look here, if we think about the same principal quantum number, so we're just comparing orbitals, it's just an orbital to orbital comparison. We're thinking about the same principal quantum number, and therefore, since the principal quantum number is not a factor, all we're thinking about now, as far as the energy level, is the effect of penetrating power. That's where, when you're talking about the energy level of an orbital, it's a function of the principal quantum number as well as the magnetic, the L, the angular momentum quantum number. That factor has to do with the penetrating power. Okay, and the penetrating power, it is largest with the S. Next most penetrating power is P, then D, then F, and so on. And so what you can imagine is when we get to, if we come back here, so you've got 4S comes before 3D. Well, 4S is, with the principal quantum number of 4, that's a larger orbital than principal quantum number 3. But what happens is the penetrating power of the s orbital can overcome this discrepancy in distance. So this is a lower energy than 3D. But if you just think about the hydrogen atom, there is no shielding. For all other atoms other than hydrogen, there's that 1s electron, there's at least one electron, the 1s electron doing shielding. And that's why for multi-electron atoms, you have to use this configuration, you have to use this energy level order. But for a hydrogen atom, you can have the electron move to excited states, but there's no shielding. So all you're looking at is the principal quantum number. That's it. right? So you can see the penetrating power of D is less than S and even less than P. Because the stability of an electron is determined by the strength of its attraction to the nucleus, it follows that a 2s electron will be lower in energy than a 2p electron. Okay, to put it another way, less energy is required to remove a 2p electron than a 2s electron because a 2p electron is not held quite as strongly by the nucleus. The hydrogen atom has only one electron and therefore is without such a shielding effect. All right, continuing our discussion of atoms, of the first 10 elements, we go next to beryllium with atomic number 4. The ground state electron configuration of beryllium is 1s2, 2s2, like shown here. You just add an electron with opposite spin to the 2s orbital. Beryllium is diamagnetic, as we would expect. It's you don't put beryllium into a machine that tests for magnetism and find that it's all of a sudden strongly attracted by a magnet. It's not. It's diamagnetic. It's not magnetic or slightly repelled by a magnet, whatever. I'm not sure what they're saying there. The electron configuration of boron, Z is equal to 5, is 1s2, 2s2, 2p1. And so you can see as these electron configurations, you're writing out, you're accounting for all of the electrons. 1s2, 2 electrons in the 1s orbital. 2s2, 2 electrons in the 2s orbital. 2p1, 1 electron in the 2p orbital. And you might be thinking, well, how do we know which orbitals are available for each quantum number? Well, we talked about that. For certain quantum numbers, you can only have certain L values in that quantum number, right? For n is equal to 2, you can have 2 minus 1, which is 1, so you can have a 0 orbital and a 1 orbital. 0 is an S, 1 is a P. And then you can also determine the orientations of those orbitals. So you know the orbitals for each quantum number, right? For n is equal to 1, you can only have the S orbital. So you don't do 1p. You don't do 1p. You can't have the 1p. For n is equal to 2, you can't have a 2d. So from that standpoint, you know the orbital, the available orbitals. You also know that you can have 3 possible p orbitals, right? So you can only have one s orbital, but you can have 3 p orbitals. And then you'll use the energy relations to know how to fill them. Okay, so for boron, we come to the next highest energy orbital after 2s2, and you get 2p. And there's 3 orbitals. So here's the 3 orbitals, right? You see how they did that? S's have 1 orbital. P, you have the x, y, and the z orbital. Note that the unpaired electron can be in the 2px, 2py, or 2pz orbital. The choice is completely arbitrary because the 3p orbitals are equivalent in energy. As the diagram shows, boron is paramagnetic. So this is arbitrary. Putting it here is arbitrary. You could technically put this in the px, py, or pz orbital. All right, Hund's rule. So now, as we continue, we're going to need another rule. The Pauli Exclusion Principle and filling the lowest energy position at a time is all we needed up to this point. But now, when we get past Z is equal to 5, we need another rule. The electron configuration of carbon, Z is equal to 6, is 1s2, 2s2, 2p2. And you could go all the way up to 2p6 because there's 3 orbitals. The following are different ways of distributing 2 electrons among the 3p orbitals, right? So here's why we need another rule, because there's these 3 possibilities, right? We don't violate the Pauli Exclusion Principle for any one of these possibilities. So what are we going to do? And you can think about how they figure out what to do is they look for which one gives the greatest stability, which is the lowest energy. That's what happens first, the lowest energy possibility. So the answer is provided by Hund's rule, which states that the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. Interesting. So you want to be more magnetic. All things being equal, the more magnetic, the more stable. All things being equal. The arrangement shown in C satisfies this condition. You have the greatest number of parallel spins here. In both A and B, the 2 spins cancel each other. Thus, the orbital diagram for carbon is, so here, the 2 spins cancel each other. So you always want to default towards the greatest number of parallel spins. So when we get to elements with d orbitals, you'll have 5 orbitals. So you can imagine those. You'll have a really magnetic material that has like 5 parallel spins in the d orbitals. All right. Qualitatively, we can understand why C is preferred to A. In A, the two electrons are in the same 2p orbital, and their proximity results in a greater mutual repulsion than when they occupy the two separate orbitals. So, yeah, what they're saying is you can get a sense for why this is less favorable than this or this. You have electrons in the same orbital, and you've got these two free orbitals with no electrons. So they're going to want to, at least at first, spread out. But why is this more favorable than this? And it says this is more subtle, but it can be justified on theoretical grounds, and it doesn't go any further than that. So I might post a comment about this as well and pin a comment. But what's most energetically favorable, Hund's rule, is if you can have the more parallel spins you can have, the better. Okay, now you might be wondering, well, okay, if we have a 2p or a 3p orbital and a 3d orbital, why don't we just fill up parallel spins all through the p orbital and in the d orbital, right? So when we get to higher atomic numbers, you'll have a 3p and a 3d. So you fill up parallel spins with all of those, because you have to factor in also the 3p orbital is going to be lower energy inherently than the 3d. So that factors in. Here, we talked about the orbitals of the same subshell. So like 2p, 3p, 3d, they're the same energy. All of the 3D orbitals, the 5 3D orbitals or 4D orbitals, have the same energy. Okay, so this is the configuration. This is the proper configuration, the maximum number of parallel spins, right? And so what that means is when we go to nitrogen, Z is equal to 7, you just put the electron here. Greatest number of parallel spins, Hund's rule. Okay, what about Z is equal to 8? Now all you can do is just put the electron in one of these orbitals, put it here, and don't violate the Pauli Exclusion Principle. So you put it opposite spin. Same idea here for Z is equal to 9 and Z is equal to 10. You just fill up 2p. And note, like, this is paramagnetic, this is paramagnetic. You have unpaired spins, but this is diamagnetic. All right, this section, this general rules for assigning electrons to atomic orbitals, all of this is just summarizing everything we've just talked about. This is all part of the summary. All right, so now we want to go past the 10 atoms. We just talked about the electron configuration for the first 10 atoms. Now we're going to go beyond that. Here we will extend the rules used in writing electron configurations for the first 10 elements to the rest of the elements. This process is based on the Aufbau principle. The Aufbau principle dictates that as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the atomic orbitals. Through this process, we gain a detailed knowledge of the ground state electron configurations of the elements. As we will see later, knowledge of electron configurations helps us to understand and predict the properties of the elements. It also explains why the periodic table works so well. Table 7.3 gives the ground state electron configurations of elements from hydrogen, Z is equal to 1, through the named elements up to LV, livermorium. The electron configurations of all elements except hydrogen and helium are represented by a noble gas core, which shows in brackets the noble gas element that most nearly precedes the element being considered, followed by the symbol for the highest filled subshells in the outermost shells. Notice that the electron configurations of the highest filled subshells in the outermost shells for the elements Z is equal to 11 through Z is equal to 18 follow a pattern similar to those of lithium through lithium through neon. All right. So they talk about these noble gas cores. You use these noble gas cores like this so you don't have to write out, keep the full configuration. You could just say, okay, you got the helium electron configuration, and then you continue on from there. It's not always helium, it's the nearest noble gas. You see neon, argon, here's radon. And then it says atomic number 11 through 18 is a similar pattern as 3 through 10. What do they mean by that? So 3 through 10, you're doing 2s1, 2s2, then you fill up the p orbital. And then 11 through 18, it's the same process. You fill up the s orbital and then the p orbital. So if we come to the periodic table, and you can see, look, this goes up to 102 here. That chart goes up to 116. But here's 3 through 10. You fill up the s orbitals and then the p orbitals. And then they're saying 3 through 16, I think it was, or 3 through 18 maybe. Again, same process. You fill up the s orbitals and then the p orbitals. We don't have to deal with the d orbitals until you get to this row or period 4. Yeah, so 3 lithium to neon, that was lithium to the first noble gas, or the helium is the first noble gas, lithium to the second noble gas, and then sodium to the third noble gas. And if we look here, so we go 1s, that's, you start with hydrogen and you get to the first noble gas, helium, and then you go 2s, 2p, this gets to neon, and then 3s, 3p, that gets to argon, and then now we get to the d orbitals. 4s, 3d, you see? As mentioned in section 7.7, the 4s subshell is filled before the 3d subshell in a mini electron atom. Thus, the electron configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. You don't go to 3d. You go to 4s. And then because this is the electron configuration of argon, we can simplify the electron configuration of potassium by writing argon in brackets 4s1, that noble gas core, where this bracket argon denotes the argon core. Similarly, we can write the electron configuration of calcium as, comes after potassium, argon 4s2. The placement of the outermost electron in the 4s orbital rather than in the 3d orbital of potassium is strongly supported by experimental evidence. The following comparison also suggests that this is the correct configuration. So they're saying, that starting with the 4s instead of the 3d is supported strongly by experimental evidence. And there's also a comparison here that suggests this is correct. The chemistry of potassium is very similar to that of lithium and sodium, the first two alkali metals. The outermost electron of both lithium and sodium is in an s orbital. Therefore, we expect the last electron in potassium to occupy the 4s orbital rather than the 3d. So they're saying that we go to 4s instead of 3d, and one way you can look at how this is correct is because the chemistry of potassium is very similar to that of sodium and lithium. That's one piece of evidence, one of multiple pieces of evidence that filling that 4s subshell before the 3d is correct. All right, the elements from scandium to copper are transition metals. All right, so from scandium to copper. So these are the transition metals. You notice it says that's the pink here. Technically, these aren't. These are post-transition metals. Gray here are post-transition metals. Transition metals, so what makes something a transition metal? They either have incompletely filled D subshells or readily give rise to cations that have incompletely filled D subshells. So the idea is these, while they seem to be a part of that D orbital, they are, but because you get that completely filled D subshell, they're not technically considered transition metals because the transition metals are characterized by having incompletely filled D subshells or readily giving rise to ions or cations that have incompletely filled D shells. And these don't do that. None of these do that. It's only these in pink that do that. All right, so consider the first transition metal series from scandium through copper. In this series, additional electrons are placed in the 3D orbitals according to Hund's rule. However, there are two irregularities. The electron configuration of chromium is 4s1 3d5 and not 4s2 3d4, okay? So chromium is going to be, you would think, it would just following the pattern, you would do 4s2 and then 3d1, 2, 3, 4. But instead what happens is, so you've got the 5 D orbitals, right? Instead, you have, it's more favorable to have, so you've got 5 D orbitals and 2 S orbitals. they're close. I guess you can kind of think of they're close to the same energy level, or they're the same, or not the same energy level, but the same favorability. That's why, they have to be, because, the 4S just surpasses the 3D in stability. Well, so what happens is it's more favorable, kind of in line with Hund's rule, to take one of these electrons from the 4s orbital and make it and use it to fill that 5th d orbital, so you have 5 unpaired d orbital electrons and 2 unpaired 4s electrons. This only becomes favorable when you get to chromium and you've got that one empty orbital, so you can take that one electron and put it in that empty orbital. So it goes 4s2, 3d1, 4s2, 3d2, 4s2, 3d3, and then instead of 4s2, 3d4, you do 4s1, 3d5 for chromium. And so you have these 7 unpaired electrons. Okay, and then after chromium, we go back to the normal pattern. So when you get to manganese, you go back to, you get 4s2, and then 3d, 1, 2, 3, 4, 5. You just have, like you would expect, 4s2 and then 5 unpaired spins, unpaired electrons. And then you go 4s2, 3d6. It's the same pattern, 3d7. But then we break the pattern again for copper, whose electron configuration is 4s1, 3d10, rather than with the argon core, rather than 4s2, 3d9. So you get to copper, and you would think you would have 4s2, 3d9, but instead you take that 1s electron, or that 4s2 electron, and put it into the 3D orbital, so you get the completely filled 3D orbital. And it explains kind of why you do that. The reason for these irregularities is that a slightly greater stability is associated with the half-filled and completely filled subshells, right? So what they're saying here is, if we look here, if you have an entire subshell, so remember, a subshell is a principal quantum number combined with a L, a magnetic or a angular momentum quantum number. So a principal quantum number and an L, that's a subshell. Here you get, I think this is obvious, right? You get all of these parallel spins. You get all these unpaired spins. Hund's rule shows why you would do this, but this is a little more subtle. If you left this electron here with the 4s, what would you have? You would have a completely filled subshell, and then a incompletely filled subshell with 1 parallel spin, but with 1 unpaired spin. If you do it this way, like shown here, you have a full subshell that is unpaired, and you have a full subshell that's completely filled, right? So like you might say, well, isn't it the same thing either way? No, because the whole subshell, you would like to have full subshells that are unpaired or completely filled. For the case, if you put this electron here and remove this electron there, yeah, you have an unpaired electron, but it's not associated with the entire subshell. See the difference? Electrons in the same subshell have equal energy but different spatial distributions. Consequently, their shielding of one another is relatively small, and the electrons are more strongly attracted by the nucleus when they have the 3d5 configuration. According to Hund's rule, the orbital diagram, okay, and yeah, here's the orbital diagrams. Again, extra stability is gained in this case by having the 3D subshell completely filled. In general, here's the main statement. In general, half-filled and completely filled subshells. You see? It's not just one orbital. If you put the electron here and erase this electron, that's one orbital that's unpaired. Here, you've got an entire subshell that's unpaired and an entire subshell that's completely filled. And half-filled and completely filled subshells as a whole have extra stability. Okay, now continuing for elements zinc through krypton, the 4s and 4p subshells fill in a straightforward manner. Okay, so what they're saying is after copper, right, that's an irregular, you have 4s1 3d10. We come to zinc and we go back to normal. We go, it would be 4s2 3d10, right? And then here we come back to the normal pattern. We'll do 4s2 3d10 4p1, 4s2 3d10 4p2, 4s2 3d10 4p3, 4p4 4p5 4p6. It's a normal pattern. And then we come to period 5. Okay, so with rubidium, which is the alkali metal, in period 5, the electrons begin to enter the N is equal to 5 energy level. Okay, the electron configurations in the second transition metal series, yttrium to silver, are also irregular, but we will not be concerned with the details here. So they're saying when you get to the second transition metal series, these also have an, it's not the same pattern as, exact same pattern as we did here. These are also have their own kind of irregular pattern. But we're not going to go into the details of that here. So let's see. Here's yttrium, 4s2 or 5s2 4d1, that's normal. 5s2 4d2, okay. But now look, 5s1 4d4, that's different, right? For the first transition metal series, we stayed with 5s2 4d3, and we did 5s2 4d4, or no, then we did 5s1 4d5. So this is different. And then look here, for palladium, they don't even fill the 5s subshell. So it's different. Okay, but then you get to cadmium, and I believe it goes back from cadmium through xenon, it goes back to the normal type, everything's normal, so let's take a look. So cadmium, 4s2 or 5s2 4d10, and then 5s2 4d10 5p1, 5s2 4d10 5p2, 5s2 4d10 5p3, 4, 5, 6, yeah. And then we come to the 6th period, cesium, starting with cesium. We come here, and now we're getting into this. The f orbital is going to come into play with these elements, and remember, the way you think about this is you would slide this entire table over, or you would slide this entire region here over to the right to put these in here, right? This gets squeezed in here. So the 6th period of the periodic table begins with cesium and barium, whose electron configurations are just the 6s1, 6s2, okay? Next, we come to lanthanum. From figure 7.24, we would expect that after filling the 6s orbital, we would place additional electrons in 4f orbitals, right? They're talking about this here. 6s, next is 4f. In reality, the energies of the 5d and 5f orbitals are very close. In fact, for lanthanum, 4f is slightly higher in energy than 5d. Thus, lanthanum's electron configuration is 5s2 or 6s2 5d1, not 6s2 4f1. So you would think that take a look at this. We don't do cesium, barium, and then lutetium. Again, this is squeezed in here. We go cesium, barium, then lanthanum is next. Here, this is 57. We do this entire row, and then we come to 71. And it's saying that you would think that we would do 6s2 and then 4f1. But it's actually 6s2 5d1. Now you might be saying, well, then what's the purpose of this chart? This chart is wrong. No. So if we go take a look at the table, let's come to the main table. So here's cesium, the start of row of the 6th period. 6s1, 6s2, yes, 5d1, right? That's not in accord with that diagonal table. But this is just an irregularity. So if we keep going, here comes the 4f, and then we eventually just transition to the f orbital. F3, 4f4, right? It's 6s2, 4f3, 6s2, 4f4, 4f5, 4f6, right? So it is, in general, the next orbital after 6s is 4f. right? Look, we go all the way to 4F14, and we have an irregularity here, but this is F, all right? What comes next after 6S is 4F. And then we come to from 4F we go to 5D, like expected by that diagonal chart. It's just that there's when you get to the transition from the transition points going from like the 6S to the 4F or any transition point, there can be some irregularities. These are just irregularities. Okay, following lanthanum are the 14 elements known as the lanthanides or rare earth series. From cerium to lutetium, the rare earth metals, these are rare earth metals, the lanthanides, have incompletely filled 4F subshells or readily give rise to cations that have incompletely filled 4F subshells. So it's the exact same definition as the transition metals, but instead we're referring to, well, actually the transition metals here, it just says incompletely filled D subshells. So any D subshell with any principal quantum number, if it's incompletely filled or readily gives rise to cations that have incompletely filled D subshells, that's a transition metal. Here, the lanthanides, the rare earth metals, are just referring to incompletely filled 4F. So it's not just F orbitals in general. It's specifically 4F. Okay, so notice that difference. In this series, the added electrons are placed in 4F orbitals. After the 4F subshell is completely filled, the next... Okay, let's come back here. Notice that they're saying, technically, so this is labeled, this is the lanthanides, this pink here, this lighter pink. But technically, this is not a lanthanide, is what it's saying, because if we come to, even though its name, it has lanthanide in it, it's saying that because if we come here, 57, this doesn't have an incompletely filled 4F orbital. So that's why it's saying that that's technically, according to this statement here, the lanthanides start with cerium, which comes right after that lanthanum, and go to lutetium. They go to lutetium here. Let's check out lutetium, 71. Yeah, see, incompletely filled. Okay, no, this has a completely filled 4F orbital, but I guess it would give rise to incompletely filled 4F orbitals, cations that have incompletely filled 4F orbitals. But I think you get the idea. All right, after the 4F subshell is completely filled, the next electron enters the 5D subshell of lutetium. Note that the electron configuration of gadolinium is xenon core 6s2 4f7 5d1 rather than 6s2 4f8. Like chromium, gadolinium gains extra stability by having a half-filled subshell. Yeah, so we saw that. There's irregularities as you go through the lanthanides. There's irregularities, right? They're talking this here. You don't just keep going with the pattern. You have another irregularity. Okay, the third transition metal series. So now we're back to the transition metals. We're back here. We're here. Okay, from hafnium to gold is characterized by filling the 5D subshell. All right, then we go through the transition that transition metal series, and then we get to mercury, and there now both the 6s and 5D orbitals are filled, and the 4F orbital. Let's see. Yeah, see, mercury, you've got the 6s orbital, 6s2, the full 4F orbital filled, and the 5D orbital filled. And then let's see what happens after mercury. It's just that same pattern. That's the typical pattern. You go 6p1, 6p2, 6p3, 6p4, 6p5, 6p6 with the fully filled 6s, 4f, and 5d orbital. So then we come here. So we should just have the same pattern, 7s1, 7s2, and then we start with this series. This is the actinide series. So yeah, 7s1, 7s2, and then we start the actinide series. And you would think that if we come here, 7s, we should start with 5f, right? But we actually start with 6d, But in general, you do end up coming back to 5F, right? 5F, look, 5F, 9, 10, 11, 12. In general, it is, you are going to 5F next, but there's these irregularities. And then you come to 6D. You go from 5F, then comes 6D. Okay, but the last row of elements is the actinide series, which starts at thorium. Most of these elements are not found in nature, but have been synthesized. Actinide series starts with thorium. So I guess they didn't state this, but this would be characterized by incompletely filled 5F subshells, or readily give rise to it. So here's the actinide series. And so I'm assuming actinum doesn't have an incompletely filled 5F subshell. Yeah, see? But then neither does thorium either. So, I'm not, you'll have to look into this yourself. I'm not sure why would they include thorium then? It doesn't have an incompletely filled 5D subshell. I guess it gives, or incompletely filled 5F subshell. But I guess it makes cations that do. So, all right, with few exceptions, you should be able to write the electron configuration of any element using figure 7.24 as a guide. Elements that require particular care are the transition metals, the lanthanides, and the actinides. As we noted earlier, at larger values of the principal quantum number n, the order of subshell filling may reverse from one element to the next. Figure 7.28 groups the elements according to the type of subshell in which the outermost electrons are placed. All right, yeah, so this should give you a general idea of electron configurations. You don't have, it's not like you could go out and after this video and you're given any atom on the entire periodic table and you can write its electron configuration, because there are these irregularities. But I think we've gone through in general why the irregularities are there, and you have a better sense of how this all comes together. All right, now let's work some example problems.